Hi, I'm Alistair, and this is part of a video diary where hopefully I'm going to document the process of creating a portable escape room game in a box. Now, at the end of the last video, I got as far as showing you the box I was planning to use. It's this flight case, which is currently empty. And I also did a very basic test of the hardware and the software, which I think I might use. So the idea I've got is that there's going to be like a central processor which is going to be responsible for controlling the overall state of the game. For that I'm using an Arduino UNO here. And then sort of the individual sub-puzzles that are contained within the box, well, they're going to be controlled by their own Arduino Nano processors. And I use this software library called PJON or PJON. And that's a single wire interface. This is all tangled up. There we go. So just by connecting 5-volt ground and a single data line between all these sub-puzzles and the controller, basically what I can do is I can create like an entire escape room game in miniaturized form inside this box. And that's kind of the idea I want to continue exploring. So what I really want to do is to have the puzzles be modules which can be slotted in and out of the box somehow to make it easily configurable, changeable. The central control unit will be able to detect which modules have been detected and to adapt the game accordingly. At least that's the idea. So what I'm going to do now is to start adding some features and functionality that you'd expect an escape room game to have. And I'm going to start off by looking at that master controller. So remember, this is kind of taking the place of the escape room control software that you'd normally have in a real life escape room game. So I'm going to think about what features I want that to have. And I'm going to look at the hardware and the software and the design all at the same time, because I think it's quite hard to separate them out. So the first thing I might expect that to do is to provide a game timer and some sort of countdown display to let players know how long they've got left. And one of the other things I mentioned in the last video is that one of the factors that influences my design is what materials I've actually got available to me. So I came over and kind of had a look at my shelf of components to see what I could use as a timer display. And I came up with three kind of possible interesting alternatives. The first one is this LCD display. So this is 128 wide by 64 high, kind of a bit like a dot matrix display. This came off a 3D printer controller, I think. And what I quite like about that is it gives a kind of a retro sci-fi feel, but also this is actually capable of displaying more than just a countdown. We could actually give lines of text to the player here, so we could give instructions or kind of quite detailed feedback or icons or symbols, things like that. So that's a possible. Then I found this as well. So this is a Max 7219 display. So this is 4 8x8 LED arrays. So I thought this would be quite nice. It's a kind of like an analog timer countdown. We could have gradually the LEDs filling up or counting down as time went on in the game. And then obviously I've got a sort of a classic 4-digit 7-segment display as well. And I've got, this is quite a nice big chunky one. So this would be quite a centerpiece, I think, of the controller. And now obviously this only displays the time, and it kind of gives it a bit of a feel of a bomb countdown ticking time, I think, which may or may not be the approach I want to do. But then I thought, well, what I really want to do is to actually make the controller kind of agnostic as to what the display being used is. So what I'm going to look at in a moment, hopefully, is to implement the software of a game timer and a countdown, and then add in the capability for the display of that timer to be in many different formats. The other thing I need the game controller to do, I need the ability to start and stop the display. So for that, I'm probably going to use just a simple, whoops, I'll drop it on the floor, simple arcade button to start with. you know, in the finished game, maybe I want the game to start automatically when the crate is opened. In which case, this could be attached somehow to the hinge mechanism, or maybe it would be a switch or something. I haven't got to decide. But for now, a simple push button will do. And I think for now that will probably do in terms of the hardware controller. So let's get on and write some software that will make this work. So this is the code that's running on the master device at the moment, and this was based on the PJON transmitter example. But I think what I'm actually going to do is I'm probably going to start again from scratch. I've proved that this works, and when I come to re-add in the network functionality again later, what I'll do is kind of refer back to that example and be a bit more careful about what I actually introduce. And what I'm going to do instead is basically start with the section of how I always write my code. So to do the timer function particularly, what we need to have is we need to know the time at which the starter began counting. That's going to be start time. We also, if we're going to do a countdown, we need to know how long the countdown is going to last for. So I'm going to do everything in milliseconds. So if we have, let's think about this. If we have 5 minutes, would be 5 times 60 seconds in a minute, and then 1,000 milliseconds in a second. So that is 5 minutes in milliseconds, okay? Which I'll put down as my initial countdown for the game. And then what we'll also do is we need to be able to start and stop the countdown. And so for that, we need to have the game in different states. So let's define an enum of inactive and active. So when the game is active, the countdown is going to be ticking down. When it's inactive, it's going to stop. And we will start off with the game in the inactive state. Like that. Okay, so that is enough to start us off, I think. And then in the setup function, well, let's begin the serial connection again. I think I actually deleted that from the previous code, but it's always useful to have the serial link, especially when you're testing and developing code, just to be able to check what values you're actually getting anywhere in your code. It's really convenient to have that in there somewhere. And then I think that's probably all the setup we'll have for now. What I'll do is I'll add in the library specific code that's actually going to activate those different displays. But for now, let's just get the timer function working on its own, and we can use this serial connection to test the output. So what I'm going to do in the loop function is I'm going to have different behaviors depending on the current state of the game. This is a pattern you'll have seen me use in lots of different examples in the past, this idea of a puzzle that's solved or active or being reset and things like that. This is a really common way to do it, is to have all the different values, all the different states in which the controller can be in up here, and then in your program loop, which is what runs around, you switch based on what the current state is. So the possibilities are, well, it might be that the game state is currently inactive, and if it is, what we're going to want to do is to test whether the condition has been met to make the thing start. But I'll tell you what I'll do first of all. Let's actually just add in all our possible cases here. So we've only got 2 cases at the moment, but it might be that I'll add more to them later. Now, the other thing I do need to do up here, so I've got my globals, but before that I need to add the pin which we are going to attach the button that's just going to start and stop the clock. So let me just call that button pin. I'll attach that to GPIO pin 2 for now. And then in my setup, what I'm going to need to do is to set button pin to be an input pull-up. Now, in the loop, when we're in the inactive case, what we want to do is to find out if that button has been pressed. So if the digital read of button pin is low, because this is an input pull-up, so we're going to connect it to ground when it's pressed. If that's low, what we're going to do is set the game state to be active. And that's going to sort of basically be the only action that we can do. When the game's inactive, we don't want the timer to do anything. We don't want any other inputs to do anything. The only thing we want to do is to be able to switch the game into a different state. Although what we also need to do at this point is to note down what time it is. I'll tell you what, so what I'll do is at the start of my loop, actually here, let's record what the current time is. So that's the millis function. That's going to tell us the number of milliseconds that have elapsed since the code started, and we'll just put that in current time every loop, and then when the game starts, the start time is going to be equal to the current time, and we're going to use that to kind of work out how many seconds we've got left. So that will probably do. Now if it's active, what we want to do, well, the first thing we could do is probably copy this whole code here, because we want to have this will be a toggle button, let's say, and this is going to change it back to be inactive again. I just realised I'm being inconsistent with my capitalizations, so this should be active up here. This is inactive, there we go, okay. So if it's inactive and we press the button, it becomes active. If it's active and we press the button, it becomes inactive again, and we don't need that bit there. Okay, and then we need to work out this bit about the timer. So let's have a think about this. This is a function which I've kind of written many times, and it always confuses me. I have to sort of speak out loud how I'm going to do this sum. So basically the time remaining at any point is going to be whatever the start time was. So when the counter started, which is when the game first transitioned from being inactive to active, so it's that value there, plus whatever the duration is, which is what we defined at the top. So it's going to be the start time plus 5 minutes, for example, and that's going to give us the time in the future at which the game is going to end. So from that we need to take away however much time has elapsed so far, and we're going to get that from doing the current time minus the start time. I think that's right. I always have to say that out loud. Yeah, so this will give us when the game ends, because it's going to be whenever it started plus however long it lasts, and this is going to be however much time has happened so far, because it's the time now minus the time we started. Yeah, that is right. Okay, cool. And then from that, we're going to now split that into minutes and seconds, so we can put it onto a display. And again, this is a function which I've sort of done lots of times, but I always have to think about. So to get the number of minutes, we divide by 60,000. That's the same value that I put up here, because there's 1,000 milliseconds in a second, 60 seconds in a minute. So time remaining we're counting in milliseconds. So if you divide that and then assign it to an int, that's going to be like sort of truncating, rounding down. So that will give us the number of whole minutes left. And to get the number of seconds left, what we need to do is first convert the milliseconds into seconds. We divide by 1,000, and then we do a modulo 60. So that's going to give us the remainder of that when it's divided by 60. So that's going to give us the whole number of seconds. Yeah, that's right. So what we'll do to start with, that's probably enough code for now to actually just test. So let's put serial print minutes, serial.print, oops, that, and then serial.print line, because this will be the last one there. So if we just literally do that, just check that I haven't typed anything a bit funky. No, that seems all right. And we'll upload that. Yeah, my board is connected on UNO. And now if I just show the serial monitor, I don't know what that is. Okay, why have we not got a countdown? Oh, of course, we haven't got a countdown because I initialized the state to inactive, of course. Yeah. So if I just take a wire, connect one end to T2, one end to ground, and I close the serial monitor. Okay. Well, that's not quite working either, is it? What the heck's going on there? Tell you what, I'm just going to reset that and start again while I figure out what's going on here. So I'm just touching the wires. Okay, I'm getting slightly... Oh, crikey. Right, okay. So I know what's happening here as well. So what's happening here, every time digital read of the button pin is low, it's going to active. So it then comes through to active. If the digital read of the button pin is low, which it almost certainly is because it was, you know, fractions of a millisecond ago, it's becoming inactive again, going here. So I'm kind of constantly looping between them. So obviously what I actually want to do is to test whether there is a new button press, rather than simply say that the input is being held down at the moment. I only want to you know, check that it was pressed down now and it wasn't last go. So this is often called debouncing. Now it's not actually too hard to write your own code that handles you know, kind of button presses and releases and things like that. But because I'm trying to do this sort of quickly just to get these displays up and running, I'm not going to be bothered to do that. And instead I'm just going to include a library. So this is a library which I've got, I think I've got it installed. Let me just check. So I'm looking for the bounce library. Yeah, bounce 2, here we go. So this is for debouncing switches and toggles, and basically I'm just going to include bounce2.h at the top. And now, rather than directly doing a digital read of button 2, what I'm going to do instead is to create a new bounce2 object. So let's call this button bounce, I guess. And then in the setup, as well as defining the button, what we now need to do is we need to attach that object to the button pin. Blimey, typing's all over the place there. And then in our loop function, we call the update. So this is going to update the value of this object, which is going to listen to the state of button pin. And now we don't use the digital read directly. Instead, what we can do is we can say if button bounce dot I think it's fell. So that means it was high in the previous frame and now it's low. So this is only going to get called yeah, let's try that. Okay, so it's not called bounce 2, it's called bounce. Even though the library is called bounce 2, the actual object itself is called bounce. There we go, that's better. Okay, right, now let's try loading that again. So now when I go to my serial monitor, okay, now we've got something that looks a little bit healthier. So I have got a count. And if I press my D2 connection to ground, yeah. Now why is that not working? Oh, because I'm an idiot here. I'm now comparing button bounce.fell to low. I just want to have button bounce. Let's try that again. Right, clear this out. But okay, so we've got nothing happening at all at the moment. And now, when I connect digital pin 2 to ground, Well, we've got a bit of a funky count going on. I'm not quite sure that's entirely right, actually, because I was expecting this to start at 5 minutes and count down, and we have definitely got something that is greater than 5 minutes there. It's going to 5 now, it's going to 4:59. Okay, so it is kind of counting correctly, but we have got it starting at a value that is greater than 5. Now if I just stop the button again, it is stopping. So my start-stop is working. I'm happy with that. I've obviously gone wrong somewhere in the code here. Yeah, now I know what's happening now. So the problem is we set the start time when we first when we first activated the switch, we set the start time. But if you stop it and start again several times, so now if I start it again, what's going to happen is that value there is going to jump, at least I think it's going to jump from 4:51 to, yeah, okay. Yeah, so that's not right, is it? Okay, so what I need to do is I actually need to keep track of the time that elapses while the game is paused as well. So I think, let's think, the way to do that would be to have another value here. Let's assign another unsigned long. So basically this is going to be something like pause time or something like that. And every frame in which the what I want to kind of is add to that the amount of seconds that have elapsed, don't I? So when it's inactive, I want to say that the pause time is equal to current time minus start time. But I need to do that before start time is reassigned. So let's do that before there. And let us make that a plus or equal as well. So every frame in which the game is inactive, we're going to add on to the pause time the difference between the current time and the start time. No, that's not going to work either, is it? Because every frame that goes by, we're going to be adding on more and more time. Okay, no, I've got a different idea. Let us not call it pause time at all. Let's call it something like deducted time, because that's also something we could use if we want to incur a penalty or something like that. We could actually add on an additional amount of time deducted. And what we simply need to do, let's get rid of that, is at the point we go from being active to inactive, so that's in this section here, we set to inactive as well. And we need to set the deducted time to be equal to, at this point, whatever the, let's think about this, it's going to be whatever the start time plus the duration is, so that's the time in the future, minus the time remaining. Because that's the time that has elapsed so far. No, that's completely wrong. That's the time that's elapsed so far, isn't it? Deducted time. So when we pause the game, what we want to do is keep track of how much time has elapsed so far. So that's the current time minus the start time. That's that. And then in this section here, the time remaining is going to be the start time plus the duration. So that's the time in the future, minus the time that has elapsed sort of in this go through, but then we also want to take off any deducted time that was added on from previous goes through. Now, does that work? Yes, I think that sounds better. Okay, let's try that. Let's upload that. And then we'll bring our serial monitor up.
Let's clear the output from last time. Okay, so the game starts and the game is in an inactive state at the moment. So what I'm then going to do is I'm going to connect my wire between 2 and ground just to start it off. Okay, we still got starting at a time that is greater than 5 minutes, so I've gone wrong still somewhere else. And we're counting down 5, 5, 5, 4. So what I'm going to do just in a moment, so it's going to count down to 4:59. That's all fine. But let's pause that countdown again. Okay, so something a bit funky there, and I'm just going to start and stop it a few times. And it goes back to 5:42, 5:47. That's interesting. I'm able to actually make the counter go further and further into the future. I've still got my maths funky, haven't I? Right, let's stop and think about this. Okay, so what is going on here? I've got start time. Oh, wait a minute, hang on. Time remaining is... No, wait, I don't need the start time here. The start time's too many times in this equation here. Right. The time remaining is just the total duration of the game, less the time that has elapsed so far, which is the difference in current time and start time, less however much stored time we saved from last time. Okay, that maybe looks better. Let's try that instead. Crikey, I tell you I always get these bits muddled up. Okay, that's uploaded all right. Let's get the serial monitor window open. And now if I connect D2 and ground, hey, that's better. Right, now we have a countdown that is starting at 5. It is counting down in the seconds. And hopefully if I now connect this pin again, I am able to start and stop. And I've paused it for a bit. Okay, so I'm getting a slightly funky value there. If I wait for a bit longer, I'm kind of able to jump up a little bit of time. Why am I able to jump up by restarting? If I restart quickly, can I get all the way beyond 5 minutes of time elapsed again? Okay, so something's still not right. But we're sort of making progress, and I guess this is the point I wanted to kind of to make, is that nobody gets these things right first time. You literally make mistakes and mistakes until you sort of have made enough. And why is that going back up? So time remaining is duration minus what's elapsed so far. The start time was set at the current. Yeah, the current time equal to when that was equal to that. Current time, so that's how much play time has elapsed in this playthrough. Then we have this deducted time. So deducted time, I am setting at the point. So that's just the time that has elapsed so far in this. Oh no, wait a minute, hang on, it's not that quite, is it? Because I need to, oh gosh, I need to account for the deducted time in that as well. So I need to actually, I think I need to add that in there as well, because the running total of the deducted time, sorry, that needs to be a plus. The running total of deducted time that I save each time has got to be equal to whatever I incurred on this playthrough added to whatever had already been deducted on previous playthroughs. Okay, let's start again. Right, so clear output. We are starting from a fresh slate. We are going to start our countdown. So I'm just going to touch. There we go. So we've got 4:59. So we started at 5 minutes. We're going down 1 every second. I can stop it. Ah, that's better. And now when I start it again, I am able to resume where I got to. So I'm at 4:42. If I wait for 1, 2, 3, 4, 5, start again. Oh, 4:43. No. or am I? Maybe that was just. I think maybe that was just a rounding glitch. Anyway, it'll do for now. I think what I'm going to have to do is put a note on that and say there's something still a bit funky on that. But for the time being, at least, I'm happy with that as a method of testing the displays, which was actually what I was ultimately meant to be doing this time. It's always the things that you think will be really quick actually end up taking ages. So I want to display that format a little bit better though. So let's come back here, and rather than printing it to the serial monitor like that, let us make this into a pretty format. So we'll go formatted time. And let's think this is going to be probably, so I want 2 characters as the minutes, 2 characters as the seconds, a trailing 6, and maybe a hyphen in the middle. So let's make this a 6 character array, and then I'm going to use the sprintf function. So let's formatted time. So rather than actually printing everything, this is called print function. It's not really print, it's more format a text string in a particular format. So the %02 means that I want to pad with 2 leading characters and then have a decimal value. Then I want to have a colon, so that's going to be my minutes, and then I also want 2 padded zeros in front of another decimal value. That's going to be my seconds. So if I write it like that, and now what we can do is I can replace my serial.print minutes and seconds separately with a formatted time like that. Upload that. That will hopefully make it appear nicer because I'll have the leading zeros. Sorry, so it'll always be a consistent width. I've dropped my little cable again. I really must install this button sooner rather than later, because at the moment what I'm going to do is just touch these 2 terminals each time. It's taking ages. There we go. So now we've got a better format to climb. Right, finally. Okay, so we've got a counter that we are able to start and stop. It seems like we might have a bit of funkiness in terms of losing or possibly gaining seconds when we start and stop it repeatedly. But other than that, we've got something that will test our display. So now let's get on and actually add that bit in as well. So I've got 3 different displays to try out, and I'm going to use 3 different libraries for them. So let's think about this. I probably don't want all the displays, so what I'm going to do at the top is add on some definitions to say which display I want to use. So we either will be using the 7 segment display, or we'll be using the LCD display. So that's an LCD 12864. In case you didn't notice, LCD displays are always labelled with the number of characters they're capable of displaying. So 2004 display, or it looks like 2004, is actually 20 characters across by 4 characters down. 1602 is 16 character wide, 2 characters wide. 12864 means it's 128 pixels across by 64 characters down. Just in case you didn't realise that. I know I didn't to start with. So, and then our final option is going to be our LED matrix. So those are our 3 different displays which I'm going to evaluate, and like I said, they actually have 3 different libraries associated with them. So depending on which one I've defined at the top there, let's actually just make sure I type the same thing each time. So this one uses an SPI interface, so we're going to need the SPI library. No, it doesn't. I'm telling a lie. The LCD library uses a library called UHD2lib. I think that's what it's called. .h. Yeah, there we go. So that's that one. Else, alternatively, I might be using the LED matrix. That's the one that uses SPI, and it also uses something called MDMax. So these are all libraries that you can install from the Arduino library manager. Like I said, I've kind of used them before, so I can remember right, I say remember. I can mostly remember how to use them. So I'm just kind of copying these lines here from previous experience of knowing how these work. And the last one, which I haven't put yet, is if I'm going to use the 7-segment display. And in that case, I want to include, I think it's called something like K30. Yeah, there we go. So when it turns orange like that, you know that the Arduino IDE's recognised what you've typed, which is quite useful because it means you know you've got the naming correct. So those are 3 libraries which I'm going to conditionally include depending on which of the definitions at the top there. Let's just check that I haven't typed anything wrong there. Right, it doesn't recognise that. Oh, that's because it's got a capital U probably. Hopefully it's taking a bit longer to compile, which is kind of a good thing. Normally, sort of. Maybe. Or not. Oh, crikey. There we go. Cool. Excellent. Right, so we've got 3 different libraries. Constants remain the same, but now I do need 3 different kind of global functions for the objects that are controlled these libraries. So I'm going to copy that whole section there where I defined the libraries, but now I'm going to actually declare the objects that we're going to use. So the constructor for this library, this is always a right pain to get right, so I'm just going to actually load one of the example codes. Let me just load the hello world or something. They have these horrible really long constructors like this. So I happen to know that the library I'm using is it's got an ST7920 chip. It's 128 by full frame. Yeah, it's that one I think. So I'm going to copy out that constructor and put it in here. Now the pin I'm going to use for that one, let's plug that one into pin 9 and put reset on 8. Oh dear, if I'm using the LED matrix, now that is going to use the MD Parola library. So we'll do LED matrix equals MD Parola, and the parameters to that, the first one is the type of chipset which I'm going to use. So in this case I'm using the IC Station HW. There's kind of a couple of different versions of very similar looking MAX 7219 displays, and some of them are kind of wired backwards, or they make the text a bit mirrored and things like that. So this parameter here, I just happen to know that my ones are using that, but it's worth changing that if it doesn't behave correctly. And for this is a nice simple constructor. This is just display 7seg, and this is an I2C connection, so we have to give the address there. So these two are both using SPI, so we have to give the pin that we're going to attach the chip select wire to, the slave select wire. This one is I2C, so we give the address of the board on the interface like that. And then, so that's declaring the objects. Then we'll go into setup, and what we'll do is we'll actually start all those objects now. In fact, so I called it that's because I copied it in from the example library, isn't it? So let's just be a bit more consistent. So basically, as time goes on, my very first rough draft through the code, I just try to get it to work, and then with each kind of iteration I try to make it slightly more better structured and more coded and things like that. So on this pass through, I'm actually going to make sure that I do change the names of my objects to be something relatively sensible. In each one, all I'm going to do is call the not the being method, that's wrong, the begin method, like that. So we'll go begin. There we go. And then finally, so we've done the definitions. Then based on the definitions, I've done the including the right libraries. And then based on the definitions, I've done including creating objects for all of them. Then I've done the setup for all of them, which is a begin method. And now what we need to do is we actually need to put the bit that updates the value. So I've already got this formatted time method now. And rather than send it to serial.print, what I'm going to do is to put these the code that's going to write to these different displays instead. So for the LED matrix, that's a nice simple one because the library for that has a function called display time in it. So we'll just pass it the minutes and the seconds. The 7-segment display. No, I've done it wrong again, haven't I? I've got these muddled up. That one is that one. That goes there. The LED matrix, that's the one that is what is that? Can't actually remember how that works. Come back to that in a minute. Right, we'll go to this one. So this is the display LED. So we're going to clear the buffer for this first of all. Then we are going to we need to choose a font to use. So we're going to call set font, and so there's loads of different fonts of different sizes and kind of whether they're transparent and whether they include like additional characters and things like that. I'm going to go for I hope it's called that one, but that hasn't come up as anything recognised, and that's because I've got a spelling mistake there. There we go. So this is telling it it's a font from the U8G2 library. Logosos is the name of the font. It's a 16-point font. It's transparent, and the R says that it's a reduced character set, so it doesn't include all of the extra kind of non-ASCII characters and things like that on the end, which just would take up more memory. So now what we're going to do is we'll draw a string, and where are we going to draw the string? Let's offset it by 10, 16, because what I'm going to do is I'm going to specify the bottom left hand corner of where we're going to write the text, and if this is a 16-point font, I need to actually be at least 16 points down the screen, or else I'm going to chop it off the top. Let's do formatted time. And then what do we do after that? Then we actually have to pass that to the buffer, don't we? So let's send to the buffer. There we go. So that is the code for that one. That is code for the LED matrix. I cannot remember what the syntax for that one is. So once again, I'm just going to load a demo. Oh look, there's a demo called display time. Oh, no, it is just display time, is it? There we go. That's not as hard as I thought it was. In that case, I've got the LED matrix one then, haven't I? Why am I completely incapable of getting these two kind of the right way around? Let me just compile that. Yeah, sure enough, that has no member called that because I've written completely the wrong thing. For this one, it is just simply print. There we go. And it's printing the formatted time. Hooray! Okay, so we are there. Although we have got a warning that says low memory available, stability problems may occur. And that is because at the moment I am basically trying to use all three displays at the same time. They all come with a bunch of libraries they have to use. This one particularly is a big old library. So that's something I need to bear in mind. And actually, having said that I was going to chop out the networking code at the beginning, I should probably put that back in again because I need to know how much memory that is going to occupy as well. It might be the case that we've actually got now too much to fit on an UNO, and I'm going to have to upgrade the master control device to be a more beefy processor, so maybe either a Mega or move to a Teensy or an ESP or something like that instead. But as the Peatland library claimed to work on all those devices as well, that shouldn't be a problem. Okay, let's try uploading it and we'll actually see what happens.
So even though I'm not actually planning to run all three of those displays at the same time, the fact that just including the libraries for all three of them has caused my Arduino UNO to run out of program memory means I think I might have to revisit the decision of what to use as the master control device. So I could upgrade to an Arduino Mega. That's got more flash memory, it's got lots more outboard ports, but a more kind of modern alternative is the ESP32. Probably I'm now going to redesign the master controller to use one of these chips instead. They're faster, they've got more memory, they've got other features which might come in useful later as well, because we could use Bluetooth or Wi-Fi. The problem is, well, there's a couple of problems. The first one is that they run at 3.3 volt logic, not 5 volt logic. So what that means is I'm going to have to redesign the Pigeon network to operate at 3.3 volts, and it probably means that I want the other controllers to be 3.3 volt based process as well. So all of that stuff I did with the Arduino Nanos and the Uno, I'm probably going to want to retest that using an ESP32 as the master device, and maybe ESP8266 as the slaves. I'm not imagining the slave devices to be that complicated. I don't think they'll need the power of a 32, and something like a Wemos Mini is cheaper and probably easier to run. The other problem is that I can never ever remember what the pin outs of these is. So whenever I get like some new processor delivered, I always store them in these little boxes with a printout of any documentation that came with, so I can actually remember. And so what I'm going to do now is to so I'll use the code I've just written. I wrote it with an Arduino in mind, but it should work on an ESP32 just fine actually. And I'm going to try wiring those hardware displays to this chip instead. And if we can get them to work, then what I'll then do is go back and rewire the network to run on 3.3 volt logic as well. Now you do need to be a bit careful with these pins, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, you get 38 and 36 pin varieties of them. So I want to make sure that I am actually following the same pin out. Yeah, this is fine. This is a 32S, which is one of the 38 pins one. The other slightly annoying thing is, in my last video I mentioned the fact that when I'm prototyping I do like to use screw terminals just to quickly plug things in. I don't have any screw shields for an ESP32 board. So what I'm going to do instead is I'm going to sort of create a prototyping board with some Wago connectors, I think. So what we're going to do, let's plug in. So I'm going to need several devices sharing a ground connection. I'll tell you what, let's actually do this properly, and what I'm going to do is just make sure that that pin is shielded before I put that in, otherwise I might create an accidental short and we wouldn't want that. So I'm just going to open my box. So this is really useful to have when you create your own cable harnesses. You can buy like jumper cables and things that have been ready cut to size, but it is quite useful to be able to make your own cables as well. So I'm going to plug a ground pin into the ground there, and then I'm going to plug that into one of the pins of this Wago connector. If you're not familiar with Wago connectors, these are fantastic little devices. They are just click open and closed, and they make a really solid connection. I mean, that is good enough for production use. So I'm basically going to do that with all of the pins that I think I'm going to need to plug into another device. So I'm definitely going to need ground. I'm also going to need 3.35 volts to go to at least one device, I think. So we'll take one of these. I've run out of individual connector pieces. It's alright, I've got another box of them here. Move that out of the way. So this is just to make sure I don't accidentally short two pins together on the ESP. So we'll plug that into there. So that is going to 3.35 volts on that side of the board, and that can come out to this connector block. Got to be careful not to pinch your fingers in these, because they're quite snappy little things. So that's my 3.3 volt and my ground line. I'm also going to want a 5 volt line as well. So 5 volt is going to be the V in pin, which is down here. So we'll take a red wire for that. Again, by convention, I tend to try to use red wires for positive voltage, black for ground, and you know, blue and yellow for data. It just helps me try to avoid making silly mistakes later on. That's going to go to V in and out to this one. So this is a little bit scrappy when we first create it, but with a bit of luck, this will actually save us time later. And then, okay, so that's my power connections. Basically, I've got ground, I've got 3.3, and I've got 5 volts. Now I'm hoping that this is going to power the displays correctly. I think they are both 3.3 volt and 5 volt sort of logic level compatible, but we'll find out in a minute. Now, 2 of the displays use an SPI connection, the matrix LED display and also the LCDs. So pull those over, this one and this one, both use an SPI connection. Now normally you've got to be a bit careful when you're using SPI interfaces between a potentially 5 volt device and a 3.3 volt device. You need to be a bit careful, because when you send signals from the 3.3 volt device to a 5 volt device, well, that's okay because that's within the tolerance level, and a high 3.3 volt signal will generally still be registered as a high signal by a 5 volt device. What you need to be careful of is when you're sending data the other way, say on the master in slave out line, because these will be sending 5 volt high signals back, which will be outside the tolerance of the pins on the processor, so they might blow it. However, in this case, I think I'm going to be okay, because looking at these boards, neither of them actually need to send any messages back to the processor. You know, a display is kind of an end point, really, isn't it? So you've got the processor sending 3.3 volt signals to the boards. There's nothing for them to send back. So we can see that this one's actually labelled. So it's got clock, chip select, data in, ground, and VCC. There isn't a data back line, so I think it's going to be okay. So what we're going to do is we're going to, so I can do my VCC and ground already, can't I? So I'm going to plug my VCC. So this is going to go to the 5 volt supply, which is here. That's going to my V in pin. Then I've got ground. That's going to go to ground. So it's going to end up being sort of a bit of a rat's nest of wires, but so long as it works to actually test the displays are working, that's good enough. Okay, now I've got clock, CS and data, so I haven't yet pulled those pins out onto Waygate boards, so let's do that now. So we are going to want the VSPI system clock line, which is GPIO 16, which is here, and hopefully we can actually see that labelled on the board here. It's the one that is sort of 2 below that ground line there. That's a little bit hard to see. So for clock signals, I normally use yellow cables. So let's find a yellow cable. There's one. And in fact, I tell you what, because I can see that I'm going to need, oh no, I'm not going to need meso, am I? So let's just leave that back. I was going to plug 2 cables into a dual sided harness, but actually I don't need to do that. Let's plug that one in there, and so that goes into P16, which is there, and let's bring that out to its own Waygate connector. Like that. And now what we can do is we can plug the clock line from this display into that clock there. And then I'm going to carry on doing that with the other SPI pins as well. So we need I'm going to start to have to use one side of these pins. So I've got Mozzie and I've got system clock, and I'm going to need them both. And in fact, I've got the ground line at the top here. So I'm going to need these 3 pins all in a row at the top. I'm going to need plugged in. So what I might do actually is swap that connector at the top, because I'm running low of these little things here, and I do want to make sure I don't accidentally create any shots on the board. So this is a little 3-way pin instead. So let's take that one out, and we're just going to pull that cable out of there. This can be a bit fiddly to do, and I'm just going to do it with the help of a little screwdriver here. If I just lift that flap up and pull this wire out at the same time, there we go. Instead, I'm now going to plug that into one end of a 3-pin connector, like that. So the one below that I now want to be the SPI Mozzie line, so I'm going to use a blue cable for that. Try and push that in. Looks like that one hasn't quite been crimped correctly actually, so I'm just going to give that a bit of a squeeze with the pliers. Give that another go. There we go, that's better. Lovely. Okay, and then the next one down is going to be the I2C clock line. Now this is going to get confusing because we've got 2 different clock lines going on. We've got the SPI clock line, which is going to these 2 devices, but then we've also got this display, and this uses the I2C interface as well. So I've got another clock line here, which is also yellow, but I need to just be a bit careful I don't muddle those up. Now typically this has already got a connector on the end of it, so we'll just take that off and we will plug that into the next slot down instead. All the way. Cool. Right, okay, so now I can fix that back on here, make sure I get it the right way around. Okay, so we've now got this line here, which is going to go to another Wago connector over here. And then we can plug the data in line of that into here. And then finally what we have, the only undone connector on this one so far is the chip select line. So this is something that needs to be unique for every device on an SPI interface. It needs to actually have a physical wire that can be pulled low to say that that device is going to communicate. Now typically this is currently a bare wire ending at the moment, and I need to plug it into a pin, so I'm just going to quickly in fact, you know what, I could even be really lazy because I have another wire here that's got a bare wire interface at one end and a DuPont pin at the end of it. So what I'm going to do is find just a 2-wire Wago connector here. So what this is going to enable me to do is take this bare end wire here, plug it into one side of that, push that down, and then take this other wire here, push it into the other end, click that down, and now that's given me the connector I want. So let's choose a chip select line here. I simply want to have a pin that's not being used for anything else. So maybe we'll go for one of these ones down the bottom here. Let's go for GPIO 11, which is next to V in. Yeah, that's right. Put that there. Now that one's going to be okay because it's next to a shielded cable at the moment. I'll put another one on that one in a minute. So this is all connected. And this one I need to plug in this ground line and this power line here. So, no, you be careful here. So the V here on this display, we've got the plus 5 volts, which is actually what's going to be used to power the LED, but we also have a voltage that the input output is going to be at. And that's going to be the 3.3 volt line. So we were taking that out to this display here. And this is a bit lazy, I should probably do this properly, but I'm just going to plug that into there and snap that down. And then we've got 5 volts. Typical 5 volts has got a shrouded end on it, hasn't it? Let's take that off. Goes to this one. Ground. We'll put over the ground one. Here's the ground one. This is the SDA, so this is the data line, which goes to here. And what was that? Oh, that's the clock line. Oh, blimey! You know what? I nearly made a mistake there. You know, after I've said it out loud, I then literally did the mistake which I was hoping not to make. So I did say that I had 2 clock and 2 data lines, didn't I? Because this one is using an I2C interface, and I've just plugged the data line into the Wago block, which has got the data for my SPI interface instead. So we want this one to go to SDA line for I2C. That is on GPIO pin 21. Which is on this side of the board, so I've also got to turn the board around a few times. So that is pin 21. Yeah, I think that's right. Let's just count there. So we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Pin 21 SDA. Yeah, cool. Phew, right, I was lucky escape. Right, okay, so we have got 2 of our boards plugged in correctly now. Now we just need to do this final one. And this is a bit of a pain to have to do. So basically these LCD boards have got a ton of different output pins on the bottom of them, but you don't actually need to use them all. That's because there's kind of a couple of different options for the way that you wire these in. There's a serial interface and a parallel interface, and we're going to use the slightly simpler one, which is a serial interface, which is what I've done before. Right, there we go. That is ugly as anything, but what that hopefully has is we have our LED 7-segment display that's got an I2C backpack into it and is being powered. It's got a 5-volt power supply to actually power the LED segments, but it's got 3.3 volt logic on an I2C interface. We've got the LED matrix display here. That too has got 5 volts going into it and is using an SPI interface at 3.3 volt logic as well. And because we've only got signals going into it, I think that'll be right. And then we've also got an LCD here that is also running an SPI interface, but it's got slightly more complicated wires. It's got the back display and everything like here. That's all coming off my ESP32 here. Where I've got pins that have had to be shared between those devices, I'm running them through these Wago connectors. So if you ignore that mess of wires in the middle, I think that should be good. Now what I need to do, obviously, is I need to go back and edit the code slightly, because when I wrote the code, I had in mind I was going to be running an Arduino UNO. Now that I'm using an ESP32, I've got to change the pins slightly. So I'll quickly go and do that, and then we'll try it out. Okay, so moment of truth. How do you plug that in the right around? Look at that. So we've got, that was the wrong around obviously, but with a little bit of juggling, we've got 3 different displays. Still don't know really which one I like best. So they can have slightly different styles to them, but they're actually all displaying the countdown correctly. So actually pretty pleased with that. Yeah, cool.